Today, we are doing continuity and end behavior. Now, this is kind of like our first steps really into calculus. So this is where pre-calculus is truly pre-calc. Okay? So continuity itself is a pretty easy idea. Literally, it means, do you have to, absolutely have to, pick up your pencil or pen to draw that graph? That's what continuity is all about. If you can just draw it in one fell swoop, one nice continuous line, continuous. If you have to pick up your pencil at any point in time to put it back down, that is discontinuous. Now, there are a couple of different types of discontinuities. Okay, and again, they should make sense as to where they get their names from. So you don't have this on your notes, but that's okay because it's just generally talking about this. So there are three different types of discontinuity. I have to pick up my pen here to draw this graph. Just like I did with my finger, I have to go up and draw it out to here. That is discontinuous. This here is an asymptote. Asymptotes go on to infinity. These are called infinite discontinuities. Because we call them infinite because you're actually never going to stop drawing this line. It goes on infinity. But then you'll somehow have to pick it up to go to the other side of the graph. Now, an infinite discontinuity does not have to go in two different directions. It could both go in the same direction. Anytime you have an asymptote involved, it is an infinite discontinuity. Now, to move from that guy to draw the next guy, I have to pick up my pencil, put it back down, and graph over here. My pencil has to jump from this point to this point in order to draw. Jump discontinuity. It just picks it up, puts it back down, and keeps going. This here is a jump discontinuity. This is a jump discontinuity. They can have open circles. They can have one open, one closed. Doesn't matter. To get from this guy to this guy, I have to pick my pen up. And the last one is one that people tend to forget the most, is what happens when we have a hole. So I'm drawing, and then all of a sudden the floor fell out. There's this gigantic pothole in the middle of my graph. Got to pick it up to draw it again. Because if I draw it in, it's going to disappear. This guy is called a removable or replaceable discontinuity, because just like potholes, if you care enough, you can plaster over it and make it go away. All you need is like to fill in that little spot, and it's gone. So that's why it's a removable discontinuity. We can deal with it. There's nothing that I can put here to make that spot go away. There's nothing I can put here to make that spot go away. So those are our three types of discontinuities. So far, so good? And just a little bit of a side note, when it comes to increasing and decreasing, I think y'all know what increasing and decreasing means, but just to make sure. So, I don't have my pink highlight. See, this is why I don't let my highlighters and stuff go out. Okay, so my graph is increasing. I'm just throwing my mic pack all over the place. When moving from left to the right, it is going up. Always from the left to the right. My graph is going to be decreasing when moving from the left to the right. It's going downhill. Always from the left to the right, because technically your perspective can change on that. If I turn around and went backwards, it's a whole different story. So if we look at this graph here, what am I doing here? Decreasing. My graph is decreasing along that interval. What's it doing here? It is still decreasing. We just have to pick my pen up and move it infinitely high because it's an infinite discontinuity, but then it comes back to decreasing. Then I'm jumping. What am I doing here? I'm increasing here. I'm jumping. What am I doing here? Decreasing along that whole thing, except for, boop, my hole. Easy peasy? Yarp. Oh, you guys are having so much fun today. I mean, you need to contain your excitement here. It is nasty out. You're nasty all the time. It doesn't really make sense, but okay. Sorry about that. You're sweet. All right, so let's tackle each of these discontinuities, shall we? The first guy, our infinite discontinuities. Again, they come to us from asymptotes. So if I have an asymptote at all, anywhere, I am going to have an infinite discontinuity. Okay? So actually, I lied. I need you guys to go grab a calculator. Sorry, Rahul. I lied to you. Did I lie to you, baby? Did I lie to you? The answer to that question is yes. Yes, you did. Grab those handy-dandy calculators. So this here is the only time we're going to be using our calculators today, just to get you to have an idea of what is going on here. So all I want you to do, I want you to go to your y equals, and I want you to type in the equation. You can either do 2 divided by parenthesis x plus 3, enter, or you can do alpha y equals and do 2 over, it's not plugged in, over x plus 3. Okay, either one is okay. Y'all good on that? All right. Now, these graphs have been used by stats, and they're all funky wonky. So I want you to go to zoom, and then just do zoom 6. Why do I have another line on that? Okay. Here we go. Do you see what I've got? Everybody got what I got? So now what I want you to do is I want you to hit second graph to get your table. Now, because when I looked at my y equals, I used that alpha y equals, I used the fancy fraction. If I look at my table is in fractions. You can make that go away because sometimes it's easier to graph with decimals. If you hit mode and you went for your, where is it? Answers in decimal form. Just makes it a little bit easier to graph sometimes. So what I'm going to do is I'm going to plot a few points. And I'm using my graphing calculator to help me do this. Do you see something right off the bat? Error. So that error is when x is equal to -3. If I look at my graph, what's happening when x is equal to -3? This one here has an asymptote. So I'm going to plot my asymptote on my graph where x equals -3. That's my asymptote. And then I'm going to go back to my table, so second graph, and I'm going to use this to pick some nice points. So I see here at -5, it is at -1. At -4, it's at -2. Then I hit the error. And actually, let's do this. Up here's another nice one. At -7, it's at -1/2. And if I keep looking at that, these numbers are getting smaller and smaller and smaller, closer and closer to 0, but it's not quite reaching 0 yet. So what that means is I actually have another asymptote. It's just a horizontal asymptote. So there's that side of the graph. And then I'm going to go to the other side. So I have at -2, I'm at +2. -1, I'm at +1. Let's see here. +1, it's at 1/2. And yet again, it's going to get closer and closer and closer to my axis, but not actually touch it, because that's, again, my asymptote there. When we're talking about continuity, we're really talking about domain restrictions. And if you think back to when we first did stuff like this, we said we had some restrictions on my domain. We said x cannot be equal to what? -3. And x cannot be -3 because at that point I would be dividing by 0. At that point I have an asymptote. So this here is an infinite discontinuity. So this is infinite discontinuity at x equals -3. So what I'd like you guys to do is I want you to go ahead and into your calculator, plug in the graph for number 2, or plug in the equation, and see what it looks like. Yep, some of these guys are going to look pretty weird. It's cute. I'm making fun of you. It's easy. All right. So hopefully you got a graph that looks something like that. You all okay with that? All on the same page? Whoop, here we go. Now, I went ahead and I was able, before I even started, because I remember my restrictions. I have restrictions here where the denominator cannot be equal to 0. So I'm going to have asymptotes, and it's my infinite discontinuity at x equals 2 and x equals -2. Please pay attention. I didn't write those as x equals 2, comma -2. They're two separate lines, so we have to write them as lines. Okay? And then to make sure this graphs nicely, all I need to do is go to my table again and try to find some nice points. So actually it looks kind of weird here. So my nicest points I see are at -4, 0. I have a -1, -1. I have a 0, -1. And things get kind of weird, so I'm going to have to put in some others. So at -3, I'm at 0.2. Let's see here, -6. What happens? So all I'm doing is I'm looking through this guy here, and I'm seeing, okay, it's going to get closer and closer and closer to 0, but it's not going to quite touch. So I'm going to take my graph. I'm going to make that happen. So this guy is a little weird. You can see here it's going to go this way. And straight up for one infinite asymptote. This one's a little bit stranger. The middle one to me is the guy that's the weirdest. So I have -1, -1, -1 and 2/3. So right here. So this graph kind of squeezes up, bumps down, and comes around that way. Now, when you finally take calculus, if you do take it, you will see that we can gather a lot more of these characteristics from the graph, like figuring out where this maximum is, where turning points are, all that cool stuff. Calculus to me, everything comes together. And now I'm going to look on the other side. So on the other side, I see 3. I'm at 1.4. So I'm right about there. 4, I'm at 2/3. So then I'm getting closer and closer and closer, so it's going this way. How are you doing with that? Yes, ma'am. To get to the table, you're going to do second graph. Sydney, you know how to get to your table? Okay. All right. So I want you guys to do number 3. All the way start to finish. Now I want you to tell me where my discontinuity is. Check your answers with your neighbors when you think you've got it. Okay, let's take a look at it. Should have looked something like that with an infinite discontinuity at x equals 0. How are you feeling with this? Next class, we're going to actually be going back to Algebra 2 and reviewing how do we graph these things without a calculator. Okay, so that's what we're going to be doing. It's going to involve a lot of just plugging values in, which is going to be very tedious and annoying, I know. But being able to graph these guys by hand makes it so that you can understand when we get to the actual limits part. All right, so let's answer just a couple more questions. I'm going to look at this first graph right here at number 1. We're going to say where it is increasing and where it is decreasing. When we're talking about increasing and decreasing, we're talking about the domain or the x values. We want to know for which x values is my graph going to be going up or my graph going to be going down. So what is my graph doing here? Decreasing. So it decreases from where to where? Negative infinity to negative 3. What do I have on the negative 3? A parenthesis. Bless you. What is it doing here? Bless you. It is decreasing there. Now, even though I'm starting up again at negative 3, I'm not going to put a bracket. I'm going to do union, parenthesis, negative 3 to infinity. Because at 3, well, there is no piece of my graph at 3. So I can't include it. So is my graph increasing anywhere? Nope. Okay, let's look at the next one. Now, I'm going to be completely honest with you guys here. I'm not going to ask a question like this exactly on a test, simply because of this guy right in here. It gets a little confusing as to where it's increasing and where it's decreasing, but that's okay. So when I'm looking at this, what is my graph doing here? Increasing. And it's increasing from where to where? Negative 3. No, negative infinity. Like negative 3 to negative 2. What am I doing here? Increasing. And I'm going to say it's going to increase from where? Negative 2. And I'm going to say it increases until we hit about negative 1, because this all is at the same height pretty much. It technically goes up a tiny little bit, but we're not going to worry about that. So from negative 2 to negative 1. Oh, did I put it in the wrong part? I'm sorry, thank you. It is increasing again from negative 2 to pretty much negative 1. This we're going to consider it flat. Technically there is a little bit of a change in there, but to try to pinpoint exactly where the top is, you're not quite there yet. And so we're going to start at 0. We're going to turn around and decrease until we hit what? 2. Do I include 2? Nope. What about over here? What am I doing? Decreasing. So I'm unioning that with what? 2 to infinity. This guy? Right, because it starts right about there and then it decreases over here. Technically, you'd need to use calculus and some advanced math to try to figure out where exactly between those two is the peak. We're not going to worry about that. You could if you wanted to. No? Okay. All right, so then we're going to be looking at number 3. What is my graph doing here? Decreasing from where to where? And then what am I doing here? Decreasing. Again, so from 0 to infinity. But I have an infinite discontinuity here. I'm never going to be at that spot. Okay? Hopefully that's not too bad. Am I right? Okay. So a removable discontinuity, and if you look at these, for the most part, we're looking at rational functions. Things that are going to be in fraction form, because that has the most of our discontinuities out of all of our standard functions. A removable discontinuity is something that all I have to do is to take one point, one dot. If I were to put one dot right in there, I would have filled it in and it would no longer be discontinuous. I patched that hole. So if something cancels out, when you can cancel a factor, it is going to be a removable discontinuity. It's a hole. If it cancels, it's a factor. I'm sorry, if it cancels, it's a hole. So what cancels out is going to be your removable discontinuity. Whatever's left is going to be an asymptote. So let's just get to this. Guess what we're going to be doing? Graphing and factoring. Yay! So, how do I factor this top piece? So, x plus 6, x minus 2 over x minus 2. Now, if I look at my original function, we do have a restriction. X cannot be positive 2. But what happens once I factor this out? You can cancel. Those two cancel, and I'm left with x plus 6. What does that mean in the world of the graph? Let's take a look. I don't know. So let's take a look. Let's type in the whole original equation. So I'm going to type it in my pretty form. X squared plus 4x minus 12. Oops. Thank you. Over x minus 2. Now that is pretty much just a straight line, right? Now I want you to go back to your y equals, and on the next line I want you to just type in what it simplified to. And graph that. What happened? It's the same thing. Let's go look at our table. Are they the same thing? They are extremely same. That's because my original graph has a discontinuity. So what I can do is I can say, all right, I'm going to graph this line. How do I graph a line?
I couldn't tell you.
You start at 6 and you go up 1 over 1. Sometimes we forget the most basic stuff. And then I'm going to go down 1 over 1. Okay. So I'm just going to draw my line here. Now that is the graph of the simplified function. It's a lot easier to graph than trying to figure out how to graph this guy here. But it didn't start off as this guy here. It started off as this. So to make them the same, we have to go and put our whole into the equation. So my whole is what happened where x was equal to 2. So I'm going to have a removable discontinuity at x equals what? 2. And when I plug 2 into my simplified version, what is 2 plus 6? 8. So at over 2 up 8, I draw my whole. And now it is the original graph. And when you do a removable discontinuity, I want to see the coordinate, because it's removable, because if I were to put a point right exactly at that coordinate, it would no longer be discontinuous. Okay, let's try the next one. What do you think we're going to do to start with here? Factor. So go ahead and factor. How does the numerator factor? X plus 3, x plus 2. How does the denominator factor? X minus 5, x plus 3. Okay, so if I look at this denominator, and I stated my restrictions, x could not be equal to 5 and negative 3. Now let's go to the graph. I'm going to type in my original function. Okay? What do you see on this graph? What do you see happening? There is an asymptote. Where is the asymptote? 5. Because if I go back to my problem here, if I were to simplify this, what would I do? Cancel out what? X plus 3's. So I'd have x plus 2 over x minus 5. Anything that's left in my denominator is going to give me an asymptote. So I have an infinite discontinuity at x equals 5, and I can put my asymptote there. But what doesn't show up on my graph, because technically holes are so very tiny, it's like Google Earth. You keep zooming in and zooming in and zooming in, and it's still going to be that tiny little dot right in the middle. You're never going to actually see it. So I have an infinite discontinuity at x equals 5. What's happening when x equals negative 3? Put a what? A removable discontinuity. So we're going to be removable, or we can think of it as a whole, at what is x? Negative 3. And to figure out what y would be, I would take that negative 3 and plug it in. What is negative 3 plus 1? Negative 1. Negative 3 minus 5? Negative 8. So at negative 3, positive 1/8, I'm going to have a whole. And let's just check to make sure that's correct. See, if I look at my table, I have an error with the -3. I have an error with the 5. On this side of the -3, I'm actually, what am I doing? I'm getting closer and closer, what looks like, to 1. So this graph is going to come this way. Where are some nice points here? Speed up, dude. And then at -2, 0, it hits the axis. At 4, we're at -6. So then it just starts to do this really big curve and come down. The 0 is supposed to be here, so it goes kind of like that. And then on the right-hand side, here's my asymptote. I'm at 6, 8, so I come all the way up here. 7, 4 1/2. 8, 3 1/3. And then it's going to take a while before I get down much further than that. Okay? So there's a graph with both removable discontinuity and an infinite discontinuity. How do we know which one's which? But looking at my equation, how do I know which one's which? The asymptote is going to be what's left. The whole is what canceled out. Okay? All right. Our last discontinuity, it does happen in all sorts of different functions. We normally see them the most in piecewise functions, but they're also, step functions are just a whole bunch of jumps. It's basically all that is, a whole bunch of jumps. So, a jump discontinuity by definition is when I'm coming from the left. So if I look at this graph, from the left, what number am I approaching? What am I going to for my y? -3. From my right, what number am I approaching? 1. Do they hit the same point? No. Coming from the left and coming from the right, they go towards different values. That's a jump discontinuity. You could be then defined anywhere in between them, or it could be open like it is here. It doesn't matter. Coming to 1 from the left, I am hitting a -3. Coming to 1 from the right, I'm getting, I don't know, that looks like either +1 or 3/4 or something like that. The way you do a discontinuity with these graphs is you can graph them. For example, if I'm going to graph that top piece here, where do I start graphing that? What is that going to be?
4.
Go start at 4, and then what do I do? Slope. And slope is going to be up 1 over 1. And then down 1 over 1. This says graph it where x is greater than 2. So at 2, this is where I'm going to start picking up my graph. So I want this side of it. Am I going to have an open or a closed circle here? Open. Yay, erasable pens. And I'm just going to connect my dots. So it goes that way. For the second graph, where am I going to start drawing it? -3. From there, where do I go? Up 2 over 1. Up 2 over 1. I can keep going. I can keep going. But where do I want to see this graph? Less than 2. So at 2, am I going to have an open or a closed circle? Closed. Beautiful, guys. And I'm going to draw which side of it? The left side. So what do I have going there? What do I have here? I have a jump. And where is my jump discontinuity? X equals 2. It's okay. I appreciate you trying. Now, you could have done that without graphing it. You want to see how you do this without graphing it? All you do is you take this number, plug it in. What is 2 plus 4? So I have the 0.26. I'm going to take this number, plug it in. 2 times 2? Minus 1? Minus 3? 1. Are those the same point? Those are not the same point. This is 2, 6. This is 2, 1. They are not the same point. That tells me there's a jump discontinuity. So I can do the same thing here. I'm going to plug in negative 1 for x. What is negative 1 squared? Minus 2. I'm going to do the same thing down here. I'm going to plug negative 1 in for x. 3 times negative 1. Negative 3 plus 2. Are those values the same or different? They're the same. So at that point, it's going to be continuous. This function here, that's a polynomial. They have no discontinuity. Same thing with this one. So I can still graph this because it asks you to kind of graph it. What function is that again? Polynomial. It is a quadratic. What shape does it have? Parabola, U shape. So I'm going to start graphing this at down 2. And 1 squared, 2 squared, 3 squared. Coming on this side also. And I only want to see that where x is less than negative 1. So am I going to have an open or closed circle? Open. And I'm only drawing that side of it. I don't need the rest of it. What kind of a function is this second equation? What's this guy? It's just a line where it crosses the y at, where's the y-intercept? Plus 2. From there we go up 3 over 1. Down 3 over 1. So at this point, negative 1, is that going to be an open or closed circle? Closed. And then it just whoop, goes right through. And so if I knew where this graph was going, I could technically draw this down, 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 down without picking up my pen or my pencil. And so this guy is continuous. Nice continuous function. Looks kind of weird, but it's continuous because there's no place where I'd actually need to pick up my pencil or my pen to draw that picture. So we have 3 graphs. We have asymptotes when you have something remaining in your denominator, which was these guys. When we had a number in the denominator, I had an asymptote. We had a removable discontinuity if I was able to cancel something out of my denominator. But if something was left, I still had an infinite. And then we did jump. So now we're going to talk about absolute end behavior. What happens at the absolute end of the graphs? And by that, I mean what's going on the far right, what's going on the far left. Are we going to a specific number? Now this table makes it look like it's going to be really difficult, doesn't it?
Yeah, sure does.
It's not. The thing that I need you to understand before I get started is this means as x goes to negative infinity, what is your graph doing? Is it going to a specific number? Is it going up? Is it going down? What's it going to? This means as x goes to the right, is it going up? Is it going down? Is it going to a specific number? What's going on? This is actually very, very easy. And the reason why, if your leading coefficient, this is what I start with. I start with my leading coefficient, and it tells me what happens on the right-hand side of my graph. Watch how easy this is. If my leading coefficient is positive, which direction is positive, up or down? Up. My graph goes up to positive infinity. If my leading coefficient is negative, what do you think I'm going to do? It's going to go down to negative infinity. To me, that's the easiest question to answer. You're going to look at it and you're going to say, this number, the number in front of your highest power on x, if it's positive, your graph ends going up. If it's negative, your graph ends going down. Then we look at the power. And we say, okay, if that power is even, it's going to start doing the same thing as it ended. So this ended going where? Positive infinity. So where is it going to start going? Positive infinity. That means my graph will go up and up on either side. And if I go to negative infinity, it's going to start going to negative infinity. Even exponents, beginning and end behavior match. What do you think odd exponents are going to do? Odd are going to be opposite. So if it's odd and it ends going up, it's going to start going down. If it ends going down, it's going to start going up. It looks a lot trickier than it actually is. What I mean by that, on number 8, what is the highest power on x? 3. So this is the only thing I need to look at. Guys, please pay very close attention, because I promise you, on tests and quizzes, I might switch up where these infinites, negatives, and positives are. You've got to pay close attention. So a negative is what's happening as it goes to the left. A positive is what's happening as it goes to the right. So, do I look at the leading coefficient or the power first? We look at the leading coefficient, because you have to decide positive or negative to start with. What is this guy? So it is going to start or end up. The leading coefficient tells you how you end. So I end going up. Then I look at my power. So the first thing you look at is your number. The second thing you look at is your power. Is that power even or odd? So it is going to start doing the same or opposite? Opposite. And just to kind of prove a point, I can do 5x to the third plus x squared minus x plus 4. And you can see on my graph, on the left, my graph is going down. On the right, my graph is going up. So for the next one, what's the highest power on x? 2. So that's the term I'm looking for. I'm always going to find where the highest power is, because sometimes it's buried inside. Which direction is this? What do I look at first? Power or number? Number. Is that number positive or negative? So it's going to end going. Then I look at the power, and it is positive. So which way am I going to go? Same, up. I want you guys to try 10 and 11 for me, please. You guys are doing really great. You got this. Almost done. Believe it or not, Jiminy flipping cricket, you're going to have a ton of time to do your homework before we leave. Yay! No. Okay. All right, can I pull up my answers? So I got negative infinity to negative infinity, infinity and negative infinity. How are you feeling on that? Okay. I didn't use the chart at all. Like, I wouldn't use the test. I normally think about positive or negative, even or odd. That's all I do. If you can do it that way, great. If you can't understand that, then yeah, you do need to memorize the table. But to me, I think the table is just too much. Okay? All right. Why are 12 and 13 different? Absolute values. What does an absolute value graph look like? It is a V. It either goes up or it goes down, but it is a V. Okay? So when we're talking about doing this with an absolute value problem, really it's not about your highest power on X. It's the sign in front of that guy. So an absolute value with a negative in front is going to do what? Open down. It's reflecting down. So what is this number going to be? Because as I go to the left, it's going to negative infinity. And as I go to the right, also negative infinity. So an absolute value is kind of like an even function. Okay, what about this one? It's got two negatives. It doesn't matter. Why doesn't it matter? Because these negatives are inside the absolute value. We don't care about them. We're caring about the overall outside piece that trumps everything else. So what are my signs going to be? Negative infinity and negative infinity. Woohoo! Bless you. Okay? Brian. That counts as your cell phone when you're doing that. Got it. All right, so that means we are done. Now it is time for your homework / classwork. Now, you don't have to graph any of these unless you want to. The goal here is going to be able to do it without a calculator. Okay? So all you need to do for these problems, tell me what type of end behavior it is. I'm sorry, no, it's not. This one is just tell me if it's continuous or not. If it's not continuous, what type of discontinuity and where is it? Same thing here. Is it continuous or not? If it is discontinuous, what type and where? Look, more of the same. And then end behavior. Okay? All right, here's we goes. Here we go, here we go, here we go again. Said here we go again.